Eric's Packing Center is a center maintained by renowned mathematician Eric Friedman about packing. I know, brilliant description. I've always wanted to contribute and have my name on this website for the whole wide world to see. So this summer I decided to give it a go, completely oblivious to the long journey of inquiry, suffering, brilliance, achievement, and loss that I will experience over the course of a month. I'm probably getting ahead of myself, so allow me to explain what packing actually is. Packing is a mathematical study of shoving as many things in the smallest box possible. For example, look at this packing of 23 circles in this square. This square has been proven to be the smallest that fits these 23 circles. Most of these records, however, don't have a proof. It's a bunch of people discovering better and better packings to experience the glory of technically having a mathematical record in their name. There are various categories of these packings, like squares and octagons, hexagons and circles, triangles, and a ton more. Side tangent, but who is this Mauricio Morandi guy? For over 15 years this guy's been contributing to the website. He has his name in every other category. I guess that's pretty cool. He must be really smart. I'm not trying to go for these packings. Most of these were discovered via code. That's kind of the only viable way to find these, and surprise, surprise, I don't know how to code. Luckily, towards the bottom lies a section labeled Related Problems. Let's take a look at tree planting. I don't understand what they're asking. Maximizing the ratio of max to min distance? What am I even looking at? That but in 3 dimensions? Nope! Maximum fence area. This could work. Basically, I could pick a number of fences that each have a length of 1, and my goal is to make a shape with the greatest area, but each fence must end on another fence, and no field can have an area greater than 1. Look at the summation for 14 fences. Here, n equals 14. See how each fence ends on another fence? The square fields have an area equal to 1, which is okay, and the triangle has an area less than 1. I should probably also note that this isn't a solution, but a discovery. Someone else can find a better shape and take the record. Quiz time! Does this configuration satisfy the challenge conditions? Yes! Each fence is connected and the field areas are less than 1. How about this one? No. This end doesn't lie on another fence. What about this one? Nope. This pentagon field has area greater than 1. This page goes up to 17 fences, and these look pretty well optimized. I wasn't sure if I could expand to greater fence numbers, so I emailed world-renowned recreational mathematician Eric Friedman, and he actually responded. Yeah, so you can expand up to 50 fences, and to submit, you gotta give me your name, picture of the solution, and an explanation until I know I can trust you. That seems pretty straightforward. Wait, what is this? Submission guidelines that have all of the information that he emailed me, making me seem like an oblivious imbecile that can't read instructions? I'm not that good at coding. I mean, I could code a clock, multiplication practice, gambling, and a program that finds the most efficient square lattices for eligible fence numbers. As you could see on the website, square grids are the most efficient when you can use them. This is because a square has a maximum possible area this problem allows, and fences can be part of multiple squares. I just wrote this program to find the fence numbers I shouldn't attempt. Most of these problems can be solved with a computer program, and the maximum fence area problem is no exception. As an amateur coder, I didn't know where to start, but I did think of this crappy algorithm. First, place a bunch of points in some random spots. Next, add the 2 fences of length 1 that connects them. Then, check if the shape follows the rules, remove redundant fences, and record the area. Then, tweak the points a little bit until the shape has more area. I keep doing this until the general idea of a shape is formed, which I can improve manually. There are a few issues with this algorithm, however. One being that I can't control the exact fence number, only the points, so I kind of have to get lucky. Number 2, I don't know how to code any of this! After locking myself in my room for a few days, I managed to implement the first 2 steps, which was very, very difficult, by the way. I had no idea where to start for the next steps. This was on a summer vacation, so I couldn't ask a professor. I'm not paying money for help, and my coding friend only speaks Java. So I completely abandoned the idea. The idea of coding, not fence. I found some patterns that can help me. On 14 fences, the triangle with a base of root 2, having the maximum area of an isosceles triangle with 2 sides length 1. I decided to call this shape with area 0.5, the hat. Any fence number 2 away from the squares can wear a hat. On number 16, you see a unique figure I called the roof. This is a trapezoid with an extra fence, keeping area under 1 per field. It's also half of a hexagon. While brainstorming ideas, if I have a unique shape like this and an extra fence, I could put it here, making the ram, with bases of root 2 over 2, giving it area of 0.25. These were pretty cool, but I wasn't satisfied. These were kind of trivial and Eric seemed to agree. I had to get creative. Some fence numbers copy the previous configuration and have a wasted fence. Look at 4 and 5, then 12 and 13. 17 and 18 would be the same, but I believe I could do better with 18 fences. I genuinely believe that polygons are the solution. Look at 9 fences discovered by Eric Friedman on his own website. Now that I think about it, he has a ton of submissions in different spots. That's crazy, it's almost like he's really good at math or something. Well, anyway, it's a hexagon. A regular hexagon. Actually, without the field area limit, the best shape for end fences would just be a regular end-sided polygon. So, I went hard at work trying to find other regular polygons I could use. If I were to use a regular pentagon, I'd have to use 6 fences at most, because the solution for 7 fences has more area than a regular pentagon. So I can't use a pentagon, hexagon's taken, and 11 fences in an attempt at a regular heptagon. Maybe I could try an octagon or nonagon? I figured out these equations for regular polygons that will help me. Looking at the graph shows that the hexagon is indeed the last polygon you could connect fences from the center with because the apothem is greater than 1. The apothem is the least distance from the center to the polygon, so if it's greater than 1, then no fences can stem from the middle to a side. Why did I write raw for the script? I'm not saying that. Maybe if I stop going outside, I'll have more time to think of brilliant ideas. Yes, that's it. The sun, a distraction. The breeze will deceive me. The grass is my enemy. An octagon must be constructed with at most 14 fences, but no matter how much I fiddled around, I couldn't find any viable structures. My inability to span fences from the center to a side is very annoying. You'd think a nonagon would have this issue, and it does, but I have an idea. I can use a maximum of 18 fences for this polygon, so I have enough fences for an interior triangle. This is huge! The only time I've gone outside these last 2 weeks was to wash a fence. Crunching the numbers shows that a regular nonagon with an interior equilateral triangle could in fact work. The problem is, I don't have any software to test it out. I only have my paper and my pencil to solve this problem, so I can't brute force a solution with a regular nonagon without tons and tons of math, because fences won't connect perfectly as apothems and circumradii I did with the hexagon. So I used a different shape, a different polygon, with the length from the side of the triangle to these 3 sides of the nonagon being 1. Knowing that this is an equilateral nonagon, I could find the shape, angles, and area with math. A lot of math. In order for this to work, I need the length from the center to this vertex to be 1 plus root 3 over 3, which is the lengths to the vertex of the triangle plus 1. I can construct 9 triangles composing this figure, 3 congruent isosceles and 6 congruent scalene triangles. Cutting an isosceles triangle down the middle gives 2 right triangles with bases 1/2 and 1 plus root 3 over 6. With the Pythagorean theorem and some simplification, the hypotenuse is root 4 plus root 3 over 3, which I call h for hypotenuse. To find this top angle of this right triangle, I took the inverse tan of 1 over 2 times 1 plus root 3 over 6, which I will call x. The central angle of the isosceles triangle is 2x. This also means that the central angle of these scalene triangles are 60 minus x. The hypotenuse of the right triangle from before is this side of the scalene triangle, and this side is obviously 1. I'm trying to find this unknown side, z. I can find this angle between z minus 1 with the law of sines, using the inverse sine of 60 degrees minus x times h. Using the angle difference identity and some simplification yields inverse sine of root 3 over 2 times cosine of x minus 1/2 of sine of x times h. Going back to our right triangle shows that cosine of x is 1 plus root 3 over 6 over h, and that sine is 1/2 over h. In our original equation, h gets cancelled out, and after some simplifying, the expression is diminished to inverse sine of root 3 over 2, which is equal to the nice number of 60 degrees. This means the angle between 1 and h is 60 plus x. Using the law of cosines, I could find z with this equation. Using similar steps, I can simplify this to 1 plus h squared minus 1 plus root 3 over 6 plus root 3 over 2. Substituting an actual value for h and simplifying yields 8 plus 4 root 3 all over 6, whose square root is 1 plus root 3 over 3. The stars have aligned! How could I be so lucky that my defined nonagon has the exact dimensions I need? Here's my complete figure. I calculated the area of each field by taking the area of this right triangle plus a scalene triangle whose area I found with Heron's formula, minus 1/6 of root 3 over 4, which is the area of the overlap of the triangle. Lo and behold, the area is less than 1. Multiplying this by 6 and adding root 3 over 4 to account for the triangle yields about 6.03. I did it! I managed to use the extra fence for 18 to make a 0.03 improvement. I knew that the color green hindered me. I sent this to Eric and he said, "Wow, 3 squares and 7 equilateral triangles. Good job." What? It was that simple? Yes, Eric Friedman, I knew that all along. I did not have 5 pages of trigonometric equations for this figure that is literally just 3 squares and 7 triangles. I would never. That doesn't really matter though. What matters is that I did it. My name for the world to see. I found the solution, and I will experience the fame to come. But this story isn't over. 4 days. 4 days. 4 days of glory. Whoa. Oh my god. Oh my god. Oh my god. My beautiful 18. Oh my god. No. No. Maurizio Morandi. Maurizio Morandi. I'm gonna get my revenge. You're absolutely cooked. Maurizio Morandi. You may not know it, but you are my arch nemesis for life. I will take a record from you. I will. I will. You cannot best me, Maurizio Morandi. You think that you're so smart. No. I am going to take a record from you. I will get my name on this page. Well, luckily I still have my backup idea for 13 fences, which is just adding these to the 8 fence figure. Wait. No. Eric Friedman had the same idea. I should have submitted it earlier. My life is ruined. Wait a second. Look at the new 18 fence figure. Mauricio? That name sounds familiar. Wait. That's the guy who's been contributing since 2008! Who even is this guy? Who does he think he is? Why don't you pick on kids your own size, buddy pal? Why would you do this to me? Get ready for a polite conversation. I'm gonna ask for your opinions on my work and constructive feedback. You should prepare for a kind and civil discussion. I will get my revenge, Mauricio. Maybe if I stop taking showers, eat every other day, and move to the basement, I'll be able to get my revenge. I won't even wash fences. They're a bad example anyway. I can't improve 18 fences. It turns out that a regular Nonagon was the play all along. Instead of just dealing with the math, I decided to play inferior games and win inferior prizes. I need to stick with convex polygons. I can just feel that they're the superior figures. Maybe it has to do with squares, not squares, but squares. A triangle with 3 sides fits in a Nonagon with 9 sides. Maybe a square could work in a hexadecagon with 16 sides? The apothem of a hexadecagon is around 2.51, but I modified it to be 2.5. Did some math, and got a figure like this. If I could split this fourth of the figure into law-abiding fields with 5 fences, then I just got the world record. But it did not work out. You know what? I'm done! I'm doing other things! It's so over. I haven't been outside for far too long, even for my standards. Maybe I'm not fit for this. Maybe Mauricio was too smart. Maybe I'm too dumb. Maybe I should just give up and move on. So with that, I went outside for the first time in what felt like a month. Probably because it was a month. It was wonderful weather, not too hot, not too cold, not too humid, not too dry. It was perfect. I meandered through the wilderness, the sun leaving each leaf translucent. Each blade of grass reflected the greenest of greens, and the sky scattered the most brilliant blue directly into my eyes. It was truly extraordinary. I could have stayed out there until sunset, but I had a brilliant idea. A brilliant fence idea. I went onto Desmos, put in a few formulas, and tested every interior polygon and exterior polygon up to 16 or something. I eventually landed on a square and a decagon. Issue number 1. The apothem is 1.53 instead of 1.5, but I could just modify the figure. Issue number 2. I can't figure out the best figure with a modified apothem as I did with the hexadecagon. I pondered this for a long while and even went on another walk, but to no avail. So I did what the most desperate do in the time of need. Ask Reddit. I have no idea what this means. It doesn't really matter though, I'll just make the length of these 2 midpoints to these vertices 1 and see where I get. Issue number 3, I only have 7 fences to spare, a really awkward number. Screw even looking designs, it doesn't have to look good, sometimes the best figures look ugly, or as I like to call them, unique. But I can't just math it out, I have to use a program of some sorts. I settled with GeoGebra because it doesn't cost $400. So I just decided to kind of brute force it, measuring each field's area with some construction techniques until I found a working solution. Finally! I sent this to Eric Friedman, my name was on the site once more! He found that my figure had an area of 6 plus root 39 over 4. How did he get this? Well, you see, I have absolutely no idea. But I do know that I can improve my submission. I'm not even being crazy this time, it's kind of obvious. I still can't figure out what they're telling me in the Reddit post. It doesn't matter though, since after some testing I've concluded that a figure with my quote, regular decagon is impossible. However, after intense trial and error, I found a similar looking solution, but optimized. I spent a long time optimizing this figure up to 5 decimal places, meaning no one can make a slight improvement to my figure and destroy my heritage! Then, after a little break, I found a 30 and 50 fence solution with the dodecagon and hexadecagon from earlier. After I realized symmetry wasn't necessary, I made this regular dodecagon with an interior hexagon, which is Eric's solution for 9 fences if you've been paying attention, and this hexadecagon with my 21 fence decagon. I soon realized that the former was beaten by this trivial shape, and I have a feeling, a lurking suspicion, that my 50 fenced figure is also faulty. But I haven't spent the time finding evidence that will crush me. In my pursuit of fence, I forgot to look at fence. The landscape has completely changed. Mauricio has taken over many values of N, but I'm not even angry. Over this whole adventure, I've learned that this isn't about glory, but progression. I know I've been hating on Mauricio, but that's just for dramatic effect. I need viewer retention. I'm actually kind of glad that he improved my 18 fences. Glad that I managed to inspire someone as brilliant as him. I'd rather there be a better solution in another's name than a worse solution in mine, for this is not about individual prestige, but cooperation to improve this somewhat meaningless problem, but nonetheless, to contribute to the ever-expanding field of mathematics. TLDR, I went crazy, touch grass.